Last time we started talking about some probability rules, some ways in which we can find the probability of something occurring in terms of other things. And one of those rules involved this assumption that all outcomes are equally likely. Say if we roll a die, there are 6 possible outcomes that we could have. We assume that each of those 6 is equally likely, and then if we have questions involving dice, we can use counting techniques to say, all right, how many ways in which can something occur, and then divide by how many total number of things can happen. Today we're talking about situations that don't follow this assumption. In other words, situations where all outcomes are not necessarily equally likely. For example, if a skilled basketball player takes a free throw shot, well, either they make it or they miss it, so there are 2 outcomes, and by the previous logic, the probability of making it should be 1 over 2, or 1/2, but that's not how free throw shooting works. Some people are better at free throws than others. There's some underlying inherent probability of making a shot. So in this case, all outcomes are not equally likely. So we can't just use our counting techniques. We have to use something else, and that's what we're talking about today. So we're working with these things called Bernoulli trials. So a Bernoulli trial is a repeatable experiment that has a few properties. Free throw shooting is a great example of this. So we are repeating a single instance, in this case taking a shot, and for each trial, one of 2 things can happen. We typically call these things success or a failure, which inherently puts some value judgment on these things, like successes are good, failures are bad. That's not necessarily the case. These are just convenient names that we give to the 2 possible outcomes. All right. So Bernoulli trials are situations where we have these repeated instances where for each instance you either have one outcome or the other, and it needs to be the case that there is some fixed probability for a success throughout the whole instance. So a success might have some probability, and then the failure would have some other probability, which is going to be 1 minus the probability of that success. Right. So we need this fixed probability, and we need it to be, each trial to be independent of the others. So we don't want it to be the case that making one free throw shot is going to change in any way the probability of making the next free throw shot. Right. So I've been using free throws as an example here. You could make the case that free throws don't necessarily meet this 3rd point, that a free throw shooter might get more confident if they are making them, or if they miss them. If they miss a shot, maybe they're getting in their own head, and then therefore they're less likely to make the next shot. A lot of weight is often put onto this notion of somebody having the hot hand, of maybe if they keep making shots, then they're more likely to make the next one. But some statistical analysis typically shows that that's not necessarily true. It's just we're recognizing patterns that we see that is just due to random chance. Right. So free throw shooting is typically a pretty good example of a Bernoulli trial. Okay. So if we have the situation where a basketball player shoots 10 free throws, a question we might ask is, what's the probability that they make 7 of these 10 free throws? All right. And let's also say that this is a fairly good free throw shooter, that the probability of making any given shot is 0.8, so 80% of shots are made, which means that 20% of shots are misses, so the probability of a success is 0.2. So let's think about how this might occur. If we're taking a total of 10 shots, then it could be the case that we make our first 7 shots, so we have a success for the first 7, and then we have a failure for the next 3. This would be a way in which we meet this criteria of making 7 of the 10. So if we want to know the probability of this happening, well, these are independent events, so the probability of making a success is 0.8, the probability of another success is 0.8, and we can go down the line multiplying these together along with the probabilities of failures being 0.2. So the product of all of these things is 0.8 to the power of the number of successes we expect, 7, times 0.2 to the power of the number of failures. So this ends up being approximately 0.0017. But this isn't the answer to the question we were asking. What we wanted was the probability that this basketball player makes 7 of 10, and what we found was the probability that they make their first 7 and then miss the next 3, which is one way of making 7 of 10, but there are other ways. So for example, we could miss the first 3 and then make our next 7. Maybe we can make the first one, miss 3, and then make 6 more, or any other version of this. So let's write out one of these. Maybe we could say, all right, we miss, and then we make the next 7. Which ends up being, well, 3 copies of 0.2 and 7 copies of 0.8. Which, since we're multiplying all these things together, is really just the same thing as this previous piece. So again, we've got approximately 0.0017 probability of this specific event occurring. This specific outcome of miss, and then 7 makes. So, if we want to know the probability of doing this, making 7 of 10, we need to add up the probabilities of doing this in all of the different ways that we can think of. So there's this one, there's this one, we can add in one more with another version of this, but for each of these instances, we're going to get out the same probability of that particular situation happening. Right? No matter what order we do it in, no matter what order we write down here, when we multiply together all of these pieces, we're going to get the same answer. We're always going to have 0.8 to the 7 times 0.2 cubed. So adding together all of the things in this list, all of the different orders in which we can do this, really amounts to saying, all right, well, how many are there? And we're just going to multiply that number by this product of probabilities. Well, we have 10 spaces, and we're trying to pick out 7 of them to be our successes. How many ways are there in which to do that? So there are 10 choose 7 ways in which to make 7 of 10. There are 10 choose 7 items in this list if we're listing out all of the different orderings to how we can accomplish this situation of making 7 of 10. This list is 10 choose 7 entries long. So if what we're after is the probability of making 7 of 10, we want to add up the probabilities of each of these possible outcomes. Well, that just amounts to multiplying 10 choose 7 times each of these things, because each of these are the same, and we get 0.8 to the 7 times 0.2 cubed. And this thing is our answer, which, by the way, ends up being about 0.01. So 20% of the time, when this basketball player takes 10 free throws, they will make 7 of those 10. All right, one notational thing before we write down a more generalized form. If I wanted to know what this probability was, rather than saying in words, what is the probability that they make 7 of 10, I can say that, all right, well, x is just some random number. So if x is the number of shots that they make, then what I'm after is the probability that the number of made shots equals 7. So this is the notation we'll use for this. We're going to use a capital X to represent whatever the random number is, or the count of the number of successes. And if we're after something like the probability of 7 successes, we write P of x equaling 7. So our answer down here is the probability that x equals 7. All right, so let's work out a general equation, a general form for this idea. So whenever we have one of these Bernoulli trials and we want to know the probability of a certain number of successes, well, it's going to always follow this pattern. there's going to be a certain number of orders in which we can get that number of successes, and a certain probability of that occurring. So this is the example that we just went through. In its more general form, the probability that the number of successes we get is some arbitrary number, so some k, so in this case k was 7, is going to be equal to the total number of attempts, or the total number of trials, choose k. So n choose k times the probability of success. So the probability of a success in our past example was 0.8. So it's 0.8 to the 7 because it was the probability of success to the power of the number of successes that we want. If we want k successes, this is going to be p to the k. And this other piece is the probability of a failure q, which remember q is 1 minus p, raised to the power of the number of failures that we want. Well, if there are n attempts and k successes, and everything is either a success or a failure, there should be n minus k failures. So this right here is the general equation for the binomial distribution. If we want to know the probability of a certain number of successes, we plug that in for k, we say n is the number of attempts, p is the probability of success, and q is the probability of failure. And then this equation gives us the probability of that number of successes. So yes, you can just use this formula, but I really wanted to dive into why exactly it does what it does. So one thing that we can do now that we have an equation like this, and this is something that we'll talk more about on Monday, and that we'll also be discussing in class on Friday, is that we can plot. So if we fix a certain n, we can plot along an axis the different values of k. So maybe we can say, all right, well, what's the probability that we have 0 successes, or 1 success, or 2 successes for a particular choice for p and q. So down here we are plotting k, or the number of successes we expect. And we can sort of scan through all of the different k's and come up with what's called a probability distribution. So maybe there's a certain probability of 0, but maybe a greater probability of 1 and an even greater probability of 2, etc. So maybe we get some bar chart that looks something like this. So this is representing all of the things that can happen. Right? If we are shooting a certain number of free throws, we can make 0, we can make all of them, or anything in between. But it's representing this with the likelihoods of each of these things occurring. The thing that we're plotting is the probability of getting that number of successes. So we're going to talk a lot more about how we can use distributions like this on Monday, but I did want to mention that, hey, this is something that we're going to be using these binomial distributions for.